Okay, now for our second hour here, I'm going to have you pull out your big books. And we're going to take a look, if you want to open up to about page 42 or so is where we're going to start. And we're going to start looking at fractions. Now, fractions seem to be the type of number that people struggle with the most. We looked at these a little bit back on Tuesday. We talked about how if we have a fraction like 3/4, that it's not two numbers. It's not a 3 and a 4. It's a single number with two parts. The 3 is the amount. We have 3 of something, just like having 3 inches or 3 cows or whatever. The 4 is the name, just like the inches or the cows. So the first thing we have to do to understand fractions is to define what a fourth is, or whatever that bottom number is, what that means. And the simplest way to do that is to go back to the old elementary school illustration of a pie or a pizza. I prefer pizza. I'm not a sweets person. Throw me a good meat pizza. A lot better. So we're going to go with pizza, darn it.
Good to me.
And now it's 8:30 in the morning and I'm hungry. But anyway, what the 4 means is we take a whole object and it gets cut into 4 pieces, 4 equal pieces. So every whole object gets broken into 4 pieces. Another way to look at it is it takes 4 of these pieces to make one whole object. So then, since we have 3 of them, of course, that means we have 3 of those objects. So again, back to that illustration, looks something like that. So our first step is to figure out how to rename it. One of the things we can do to rename that is, looking at this illustration, I just take each slice and I can cut it into equal slices. Let's say I'm going to cut each slice into 3 equal slices this time. Pretend these are equal. When I'm drawing pictures, you're going to have to do a lot of pretending. Now, how many pieces does it take to make one whole object? 12, yeah. We had 4, and each of those 4 got cut into 3 pieces. So 4 times 3 would make 12. How many pieces do we have? 9. We had 3, and each of them got cut into 3, so 3 times 3 is 9. We now have 9. That picture now illustrates 9 twelfths. Do we have any more or less pizza than we did before? No. We have exactly the same amount. 3/4 and 9 twelfths are exactly the same amount. They just look different. So we didn't change the amount, we just changed the appearance. Well, why did that work? It's because of what we did right here. We multiplied by 3/3. What does the 3 down here tell us? It takes 3 pieces to make a whole object, doesn't it? What's the top 3 tell us? We have 3 pieces. If it takes 3 to make a whole object and we have 3 pieces, that means we have one whole object. This is 1. So what we multiplied by here was 1. And when we multiply by 1, it does nothing. It does not change the value. Now it can, as we saw here, it can change the appearance, but it cannot change the value. When we look at measurement conversions later in the year, that's going to be a very important thing for us. You can multiply by something that's equivalent to 1 to convert a measurement. It doesn't change the value, just the appearance. So that idea is very important. This, by the way, is something we call a unity fraction. You don't have to memorize the word, just know the concept. A unity fraction is a fraction that has an equivalency of 1. Whatever's on top is the same value as what's on bottom, so it's equivalent to 1. And you can multiply by unity fractions in a lot of different applications to change the appearance, again, without changing the value. So let's look at something like 2/5. Of course, 2/5 means how many pieces does it take to make a whole object? 5. And we have 2. The first step in renaming a fraction is deciding what we want to rename it to. For example, maybe we want to rename this into 30/5. Now we've got to figure out how to get from fifths to 30/5. What would you multiply a 5 by to get it to a 35? 7. So that's saying we have to cut each of those pieces into 7. So what do we have to do to the top? Times 7. If we're cutting each of these 5 pieces into 7 equal pieces, the 2 that we had automatically get cut into 7 equal pieces, don't they? So that gives us 2 times 7 is 14. So let's just do it the short way here. What do we have to do to the 8 to turn it into a 40? Times 5. So we have to do the exact same thing on top. Times 5 is 15. Very good. So what I want you to do in your book on page 43. On the bottom of page 43, there, just very quickly, 1 through 11, do the odds. Give you a couple minutes to buzz through those, and then we're going to go over them, and then we'll go over another little topic. So let's just see how you did, Craig. So for number 1 there, 1/2 becomes how many 16ths? 8. Perfect. Number 3, 3/4 becomes how many 32nds? 24. Very good. Times 8 and times 8. Number 5, 7/8 becomes how many 32nds? 28. Good. Times 4, so times 4. 7, 11/16 equals how many 64s? 44. Very good. So times 4 and times 4 again. Number 9, 1/4 becomes how many 20ths? 5. Good. Times 5 and times 5. And finally, number 11. Now I realize this one's what we'll call an improper fraction in a few minutes, but 19/12 is how many 72nds? 114. Good. Anybody have any questions on doing that? Good. The next step, if I have a fraction like, pen all tangled up here, 48/64. I'm trying to visualize 64 objects, or 64 pieces to make a whole object is kind of tough. And visualizing that we have 48 of them is kind of even more difficult. The human mind, human brain, can on average can visualize between 8 and 13 things before you try to visualize more than some of the others start to fade out. Fortunately, we can change this appearance again to make it simpler to visualize and simpler to work with. Up here, we multiplied the top and bottom by the same number. So we can reverse that process. If I had 2/5 and I multiplied by 7/7 to get 14/35, I could reverse that. I could divide by 7 on top and bottom again to get back to the 2/5, right? Well, here we saw that it was multiplied by 7, so we knew it was multiplied by 7, so we knew what to divide by. The trick is to look at a problem like this, 48/64, and figure out what both can be divided by. Now, you'd asked about factoring, prime factoring. This is one of those applications. I'm not going to show you the prime factoring today. If we get a little time, I might show you, but this is one place where we can do it. Okay, 8 will divide into both of them. That's a start. 48 divided by 8 is 6. 64 divided by 8? 8. Are we done? No. Both of those can still be divided by 2. Very good. 6 divided by 2 is 3. 8 divided by 2 is 4. Now you saw 8 right away on this one. Some people won't. 8 is actually pretty good. Now if you look closer, you actually both of them could have been divided by 16, would have done it all in one step. But we don't have to do that. Many of us were taught that you have to look at those two numbers and you have to find the largest number that divides into both of them. That's a lie. You just have to find any number that divides into both of them. You could have started out here and said, hey, 48 and 64, they're both even, so I can divide them both by 2. Gives me 24/32. Hey, guess what? I can still divide them both by 2. They're both still even. 12/16. Hey, still even. Divide by 2. 6/8. Now we've been there before. We can still divide by 2. 3/4. All we have to do is find any number that will divide both of them. And just keep going until we can't do it anymore. It takes a little more work to do this. If we saw the 16 right away, we could have done it in one step and been done with it. But we still get there. That's your prime factor. It'll tell you that number. Well, in fact, if there's a little time at the end of the hour, I'll talk about prime factoring a little bit. But yeah, 48 is 2 times 2 times 2 times 2 times 3 if you factored it out. 64 is 2 times 2 times 2 times 2 times 2 times 2. Once you got it prime factored, it's just cancel out common factors. It's 3 over 2 times 2 or 3 over 4. If we have some time, we'll take a look at that at the end of the hour. So let's see here. Looking at something like this, if I want to reduce it. What can both of those be divided by? 5, okay. 60 divided by 5? 12. 105 divided by 5? 21. Are we done? No. What can we still divide by? 3. Very good. 4 over 7. Now, you can see here, once you divide by something, if I'd looked at these, it would have been kind of tough to figure out if those were divisible by 3. But once we divided by the 5 and they're smaller, it's easier to see, oh yeah, both of those are divisible by 3. That's why I say don't try to find that biggest number. Divide by something. Once you divide by something and get the number smaller, often it is easier to see that it can be divided by something else. For example, we might have 42 over 70. Looking at that, of course, it's easy to see that they can both be divided by 2, because they're both even. 21 over 35. Now, somebody said this the first time, but now that they're smaller, it's easier to see that they can both be divided by 7. 2/5. There are some very quick ways to tell if numbers can be divided by other numbers, at least certain numbers. Call them divisibility rules. That looks like to tell if a number can be divided by 2, it's an even number. In other words, it ends in 0, 2, 4, 6, or 8. You know how to tell if a number is divisible by 3? Nope. You know what the word sum means? Sum means add them up, right? Sum of the digits means you add up the digits. $5,871. To tell if that's divisible by 3, we're going to add up the digits. 5 plus 8 is 13 plus 7, 20 plus 1, 21. Is 21 divisible by 3? Yep, so then this is divisible by 3. How about here? Well, let's add up the digits. 9 plus 8, 17 plus 6, 23 plus 4, 27 plus 3, 30 plus 9, 39 plus 6 is 45. Now what if you look at that and don't know if it's divisible by 3? This is the beauty of this. What's 4 plus 5? 9. Is 9 divisible by 3? Yeah, well then 45 is divisible by 3. And then this is all divisible by 3. It's kind of neat. I mean, obviously, I'm not going to ask you 9 million. I'm not going to ask you if it's divisible by 3, but I just wanted to show you that you can actually keep going. If you get to a number here and you're still not sure, you just add them together and see if that sum is divisible by 3. What's that?
Really nice extra credit question.
Give you like some 14-digit number, something big enough that you can't enter it in your calculator. Yeah. Yeah. I've done that before on matrices. I'll give you like a 6x6 matrice. You guys don't do matrices in here. We'll give you a 6 by 6 matrix, you find the determinant. You end up with, what is it, 6, 5, 30, 120, 3 by 3 matrices. You have to do to get to it. Now for 4, there is a divisibility rule for 4, but it's not a really good one. The divisibility rule for 4 is if you take the last 2 digits, if the last 2 digits are divisible by 4, then the whole number is divisible by 4. So like 79,232. All you have to look at are these last 2 digits. Is 32 divisible by 4? Yeah, so the whole number is divisible by 4. Guess what? I don't really care. It's a lot easier to tell if something's divisible by 2. If I divide by 2 twice, guess what? I just divided by 4. So I don't care. I'll just use the 2's. One that I think you guys all just used without even realizing it is 5. And if something, to know if something's divisible by 5, it ends in 0 or 5. You got it. I think we used that one up here without even really thinking about it. You can tell those are both divisible by 5. 6. If it's divisible by both 2 and 3, it's divisible by 6. So once again, I don't care if it's divisible by 6. I'll divide by 2, then divide by 3, and I've just divided by 6. 7. As of this point, there is no rule to determine if something is divisible by 7. If in your free time at home you can come up with a rule that can be used to determine if a number is divisible by 7, and it works every time, I will give you extra credit. In fact, I will give you an A for the course. Because I'll take your rule and publish it, and I'm going to retire off of it. Because they've been looking for one for a couple hundred years now. If one of you guys find it, I have no problem giving you an A for the next 2 semesters. I'll submit your grades from the beach somewhere in the Caribbean. I'll kick back a little bit. That's what I always tell my students. You know, if you ever strike it rich, just remember who helped you get there. Just kick back a little bit. Yeah, so anyway, 8s. There's a rule for 8s as well. 8s go off the last 3 digits. So yeah, 74,104. You have to determine if 104 is divisible by 8. Well, it is, but that's not easy to determine, is it? So realistically, again, just like the 4s, I don't care about the 8s because I just divide by 2 3 times. I just divided by 8. Number 9, I could do the same thing. I just divide by 3 twice. But 9 actually does have a rule. It's the exact same rule as 3. Only if you add up the digits and it's divisible by 9. Like 7,425. 7 plus 4 is 11 plus 2, 13 plus 5, 18. Is 18 divisible by 9? Yep, so 7,425 is divisible by 9. Divisible by 10? Ends in 0. Above that, there's a lot of numbers that we don't need rules for, like 12. Because 12 you just divide by 2, 2, and 3. Or divide by 4 and 3, however you want to think about it. 15, divide by 3 and 5. 14, divide by 2, but we don't have a rule for 7. But we're stuck with it. There are rules for a lot of the prime numbers, like 11 and 13. By prime numbers, I mean they can't be divided by anything else. 12, we could divide by 2, 2, and 3. Well, 11, you can't divide by anything to make, to make up for the 11s. There are rules for many of them, but as we get larger, they get more and more complicated. I'm going to show you the rule for 11, but it's very tough. The rule for 11 goes off of every other digit. So let's say I have a number like that. 79,864,356. What I do is I start with the first digit, and I take every other digit. and add them up. 7 plus 8 is 15 plus 4 plus 5, 24, right? Then I take the other digits that are left and I add them up. 9 plus 6 plus 3 plus 6, 24. I take those two numbers and I subtract them. 24 minus 24 is 0. If that number, when I subtract those totals, is either 0 or divisible by 11, the whole number is divisible by 11. This number is divisible by 11 because that difference is 0. Now you can see that's kind of a complex process. Especially now that we have calculators, it's probably easier just to type in the number and divide by 11 and see if you get a decimal. But it's there. Okay, so kind of quickly, on page 44, in the middle of the page there, I want you to try 1 through 11, the odds again, reducing those. And we'll talk about them in just a minute. So let's see how this went. Number 1, 2 over 8 is going to reduce to 1 over 4. Good. 3, bless you. 6 over 16 can reduce to 3 over 8. 90 over 80, 9/8. Good. 7 over 28, 1/4. 48 over 64, 3/4. And 81 over 36, 9/4. Good. That 9/4 there is actually the perfect problem to bring us into our next topic here. We can run into stuff like 44 sevenths. When we run into something like that, remember the 7 is telling us it takes 7 pieces to make a whole object. Well, we have 44 pieces, which means we have enough pieces to make a whole object. We have enough pieces to make several whole objects. So it makes more sense to us to have the whole objects and then the pieces left over. What we have right here is what we call an improper fraction. Now, improper implies that there's something wrong with it. It's breaking a rule. It really isn't. There's nothing wrong with it. We just don't like having more pieces than what we need. We'd like to have whole objects instead of having that numerator bigger than the denominator. So what we're going to change it into is something called a mixed number, where we have the whole objects grouped together in whole objects and then the pieces left over. Well, our first stage would be to figure out how many whole objects we can get out of there. How would we do that? Divide. If we did 42 divided by 7, if you punch that in your calculator, you're going to get something like 6.285714286 approximately. What's that tell us? There's a remainder of something, but there's 6 whole objects. We have 6 whole objects. Now we need to figure out of those 44 pieces, how many pieces are left over? How do we know that?
7 times 6.
Well, there we go. Yeah, 7 times 6. Because each of those whole objects has 7 pieces. 7 times 6 is 42. So out of 44, there's 2 left over. Now, I did it this way to show you that if you use your calculator, it's going to give you this long decimal. And it could cause a problem. Let's look at like 39 sevenths. If we divided that on the calculator, you get 5.71428574143 approximately. Does that mean that's 5 and 7 sevenths? No, it doesn't. How many is it? Yeah, there's only 4 sevenths. Actually, I did that decimal wrong, didn't I? I divided wrong. That actually should be 5.57142857.1. Sorry about that. Either way, it's still not 5 and 5 sevenths, is it? It's 5 and 4 sevenths. What really is going on here is a division. The reason I point that is a lot of people look at this and say, oh, this first number after the decimal point, that's your 5 sevenths. It's not. Not by any means. No, yeah, if you're dealing with tenths, it would be, but sevenths, no. The way it works is a division and remainder. This would be 39 divided by 7. How many times does 7 go into 39? 5. 5 times 7 is 35. Subtracting gives us 4. There are 4 of those 7s left over. So if I were reducing something like 28/5, I'd do the same thing. 28 divided by 5. Let's rewrite that so it actually looks like an 8. 5 goes into 28. 5 times 5, 25. There are 3 pieces left over. So that's 5 3/5. If you wanted to use your calculator for this, you could either just go through the process I just went through. You do 28 divided by 5, which will give you 5.6. And then you could pull off that 5 and say, okay, now 5 times 5 is 25, and subtract to get 3 left over. There's another way you can do it that's a little bit shorter. You can divide and then you can multiply back. What I mean by that is, okay, so I'm going to do 28 divided by 5, and I get my 5.6. That's 5 whole objects. I'm just going to subtract my 5 to get my 0.6. What did I divide by in the first place? 5. So I'll multiply by 5 again to go back. So there's 3 left over. That's 3/5. To me, that's a lot of messing around with the calculator. I don't care for that much. To me, of course, I don't mind calculating by hand, so for me to do the long division with the remainder isn't such a big deal. This one, a lot of you probably could have done that in your head anyway. Let's look at one that you might not be able to do in your head. Like this one. Just a long division and remainder. 149 divided by 11. 11 doesn't go into 1, but it does go into 14 once. There are 3 left over. Bring down the 9. 11 goes into 39. 3 times. That's 33. There's 6 left over, so it's 11 and 6, or 13 and 6/11. Make sense? Okay, well, on page 40, where are we going here? 45, 46, on the bottom down there. Oops, actually, I'm going on page 46. 13 through 23. The odds. I'm going to have you try those quick, and then we'll have one more thing to do yet. Well, let's see how you did on these so far. Number 13, 14 over 5 becomes 2 4/5. Good. 63 over 4 becomes 15 3/4. 79 over 16 becomes 4 15/16. 87 over 8. 10 7/8. 318 over 32. Okay, 9 30 seconds, but you'll see there's something more we can do there. Yeah, 9 15/16. Very good. 23, 451 over 64. Perfect, 7 3/64. So that one's a tougher one. Okay, well, there are times, most of the time we want our fractions in mixed numbers like this. Because it's just easier to think of them as whole objects with the little pieces left over. But as we're doing some operations with fractions, and if we're dealing with ratios and proportions, sometimes it is easier to have the improper fraction instead of the mixed number. So if we have 7 2/3, and we want to convert this into that improper fraction, it's still going to be thirds, because we can't change the number of pieces or we could change them, but we're not going to right now. But what we need to do is we need to break this whole number, the 7, up into pieces. Well, how many pieces is it going to become? 21. How'd you get 21? Yeah, the 3 here tells us that each whole object is going to become 3 pieces. So you take the 7 whole objects times the 3, which is 21. What do we have to do with the 21? Yeah, add 2. We already had 2 pieces. We got 21 more pieces. gives us 23 total pieces. So it's 23 thirds. We might have 9 and 2/5. Well, I gotta get away from the twos. Let's do 9 and 3/5. What are we going to do? 9 times 5 is 45, plus the 3 is 48. And of course, that is still 48, still fifths. That part doesn't change. We haven't changed that at all. Or we might have 3 and 5/8. Tell me what to do. 3 times 8 is 24. Plus 5 is 29/8. Very good. So where I'm going to have you start out now is I'm going to have you look, starting back on page 45. We're going to do 1. It's actually going to go over onto page 46. 1 through 11. The odds there. Convert those mixed numbers back into improper fractions. Okay, number 1. 2 1/2 becomes 5 halves, 5 seconds. 1 5/8 becomes 13/8. 1 3/16, 19/16. On to the next page. 4 9/32. 137/32. Good. 5 31/32. 191/32. And finally, 43 4/5. Okay. 43 times 5 is 215, plus 4 is 219/5. Anybody have any questions on those? Okay. Homework for today is going to be really simple. Starting on page 47 and going to page 48. Come on. Big book. Now, I don't usually have you do the evens, but I am going to have you do 1 through 6 here. Page 47 through 48. This is basically the next page in your book. I'll give you your last 3 or 4 minutes here to work on that.